Well, thank you very much. It's very nice to be here. And thank you very much for David for this beautiful introduction on cluster categories, which I'm very happy about. Much happier than I thought I would be. Even happier than I thought I would be. So we're going to talk the title, and maybe I should say it a bit more honestly. The title of the talk is Cluster Categories and 6 subcategories. So when Robert and Henrik very kindly asked me to be part of this masterclass, I asked them, well, how do you see myself fitting in here? Is there something you'd like me to talk about? And cluster categories were mentioned. So I was like, well, that's good. I like talking about cluster categories. However, 2 years ago, I've given a masterclass here pretty much on cluster categories. So I thought I shouldn't do the same thing again. Okay. So then I was thinking, how do I get a good angle to fit it? Maybe tailor it to the interest of the audience, hopefully a little bit. And I thought 6 subcategories would be a nice way to do that. Okay, so that's how this title came about, and then I realized that's kind of like a very vague title, a very broad title. I could be talking about a lot, but I have 4 lectures, so we better focus a little bit. So what we're going to do today is maybe the part 0 is motivation. You could read that as justification, why I'm allowed to talk about the things I will talk about. We will then meet the main players, which are lattices, and specifically lattices of 6 subcategories. I'm going to talk a bit about that, important concepts, etc. And we're going to see in the next part that these lattices, specifically of 6 subcategories, can take a lot of different shapes. Sometimes they're really nicely controlled by spaces. That's what we kind of wanted to be the nicest possible thing. Sometimes they're absolutely not. So the many shapes in the poetic title, the many shapes of this lattice of 6 subcategories, which I'm just going to call T of K, whatever that means for now. Yeah. And so we say sometimes these guys are controlled by spaces, sometimes they're not. But the beautiful thing is that we can do a construction, or to do distinct construction, in fact, to always approximate such a lattice of 6 subcategories by a space. So we have some controlling spaces in the background. That's what we're going to talk about then.
What do you mean by space?
Topological space. And finally, because we should somehow respect our cluster categories, our title or cluster categories, we are going to talk about a way to unify continuous, by which I simply mean something that's controlled by a space somehow, and discrete, which I mean something that is not. We'll talk a bit more in detail about these ideas. Unified, continuous, and discrete aspects of T of K. And that's where this is a bit more of a speculative thing. I don't know how to do that more generally, but I think there should be something there. And what we're going to do is we're going to discuss this in terms of a cluster theoretic example. So what David told us about today, and it can become relevant at the end. So we have a nice bracketing after the workshop of the masterclass by these cluster categories. All right. So that's the overview. That's what we're going to do this week. And we're going to start with our motivation. And you know, for some of you, this might be the first masterclass. There's some young people here. Many of you will have been at masterclasses, summer schools, etc. before. And you know, those of you who have know what happens, right? You go to this masterclass as the title, and then there's these 2 talks that are amazing, spot on, exactly what I'm expecting, exactly what I've been hoping for. And then there's this 3rd talk, and someone's just clearly having a lot of fun talking about whatever they want. And you're like, did they even read the title of this masterclass? That could have been my talk. And it would have been if you have missed the first 15 minutes. So I'm now going to tell you how we fit here, right? So that's the mandatory 15 minutes of motivation. And so I'll tell you why you should care about clique subcategories. Specifically if you're interested in interactions between homotopy theory and representation theory, right? And the motivation perhaps, so right, that's what we want. We want some interaction. Just to remind everyone why we're here, between homotopy theory and representation theory. And what we're going to do is we're going to look at some ring A. And what I'm going to do is I'm going to take the polynomial ring in two variables, and I'm going to mod out by x cubed and y cubed. All right, so this is a commutative ring. Fantastic. And what can we do when we have a commutative ring? We can study its localizations. But wait, Sira, you will say, that's not very fun here. Yeah, why is that not very fun? There's not really any interesting localizations here, right? No interesting localizations. Because if you look at it, it's too nilpotent. Yeah, x is nilpotent, y is nilpotent. But if you look at the spec of that ring, it's just a single point. The ideal generated by x and y. Okay, so we should stop here or what? I don't know. Then we can do more. Right, so you could think, okay, we don't just have localizations, we have universal localizations a la cone, right? But sadly, also no interesting universal, more universal approximation exist. Also, no more interesting universal localizations in the sense of cone, where you now would, instead of inverting elements of the ring, you would want to make some matrices invertible, or if you want some maps between projectives. Still, you can't really do that, because somehow if you wanted that, any universal localization in this sense should give you a localization of perf of A, of the category of the perfect derived category of A, yeah? I put that up. Oh, yeah, I'm used to these August quotes that move together. Anyway, I'm very happy. Good blackboards. In fact, if we pass to perf of A, this has no interesting localizations, but this is a triangular category now. Right? And I say this has no interesting localizations. What does it mean to be a localization of perf of A? It means you invert some maps. Yeah. And what does it mean to invert a map in a triangulated category? We have some map between these perfect complexes. What does that mean? Well, we want to make that map an isomorphism. And what does it mean to be an isomorphism in a triangulated category? It means that your cone vanishes. So what we're really doing, and we're going to talk a little bit about that later, again, so this is just part of the motivation. Many of these ideas are going to show up in detail, but that's the same as sending the cone of f to be 0. Yeah? So, because f is an isomorphism, if and only if the cone vanishes. So if you want to force it to become an isomorphism, you can just force the cone to become 0. Good. So, if if we think about it that way, the exact localizations the localizations of curve of A, they correspond to the collections of objects that get sent to 0 when we invert maps which have those objects as a cone. Now if you want, you have your first pseudo definition of a 6 subcategory. These are 6 subcategories of curve of A. Right, so unfortunately, we have a celebrated result due to Hopkins and Lehmann, and then maybe in the generality you're going to write it generalized by Thomason for any commutative ring. So Hopkins Lehmann just did it for commutative in theory, and Thomason then for any commutative ring. You have a commutative ring. And if you look at the classification, if you look at the collection of 6 subcategories of curve of R, these are the things we want if we study localizations. These are precisely given. Well, this is somehow parameterized by stuff in spec of the ring. So I'm just going to write it a bit lazily. We're going to have a more formal statement later. These are nice subsets of spec R. Okay. Now we go back to our A. And we see spec A is a point. There's not many nice subsets of spec A. There's only 2 subsets of spec A. And these are precisely all the ones we get here. So the lattice of 6 subcategories, words we're going to talk about later, here is precisely the lattice with 2 elements. So maybe I should write that down. As I said, that the localizations of curve R are controlled by those of R. Okay. Right, so if we already start, with a ring that doesn't, a commutative ring that doesn't have interesting localizations, we can't really hope to get interesting localizations of curve of R. Okay, so no universal localization interesting. Should we give up now? Well, of course not. Yeah. So we should just pass to something a bit bigger. And what we could do is we could look at the bounded derived categories of finitely generated modules over R. So maybe I should write that down. I said it. The lattice of whatever that means, the set of 6 subcategories of curve of A is really just 0 and curve of A. You're always going to find these 2 in a non-zero triangulated category. The whole thing at 0, okay, these are there, but nothing actually interesting is there.
Does the nice internal include open?
So again?
Does the nice internal include
no. Open of something. We're going to come back to that later, but not of spectral. It includes close. So it's kind of the other way around. But we'll talk about that in detail. Excellent question. It has to do with the topology of spectral. Good. I mean, in this example, okay, yes. In this example, sure, everything you say is going to be true, basically. But not in general. Okay. So, more interesting. dB of 1. Okay, so one thing that maybe we note is that if we intersect curve of A with just the module category of A, that is really boring because the only guys we're going to find are 3 guys. So this is just add A. Okay, so not much is happening here. However, like mod A is wild. It has a lot of stuff happening. I mean, okay, to be completely honest, perf A is also wild, but let's just pretend we didn't care about that. But mod A is really a big thing, and it sits inside B mod A. Yeah, so it gives us interesting stuff to play around with.
Sira,
yes.
Does this intersection also include modules of finite projective dimension?
Sorry. What?
This intersection, right?
Yes, finitely generated modules of finite projective dimension.
Okay, yeah. But so not just add A then? Or, I'm sorry, is add A taken, add A needs 3 modules?
Add A is 3 modules, but this is really all you get here because you work with a local ring.
Okay.
Yeah, I mean, it's a special situation.
Yeah, so
Normally you get more, yeah. No, you get, yeah. Okay. This is wild. Yeah, okay, this is wild, we said that. So, what happens now if we look at proper-stick subcategories of that? Okay, so this, okay, this is not obvious, but I'll tell you. This is due to Stevenson. You can classify those things, and these are precisely collections of closed points. Of the projective line. Alright, so that's a little bit more interesting. There's more that can happen here. But how does that write as localizations? Well, we should think of these stick subcategories just as before, right? The sets of stuff we send to 0. So these are going to give some, like, this corresponds to inverting certain maps in DP mod A. But actually, it corresponds, in some sense, to localizations of a differential graded algebra. Right? So this guy here is generated by the unique simple K. So by tilting, it's just perf of R home from K to K. Yeah? So if we just said when we have perf of something, right? These are the localizations somehow, the derived localization in that case, right? Of that thing. So these are just, but these are the localizations of perf of that EGA. These are just the derived localizations of Ahon array from K to K. And that thing is now uncomplicated. It's a non-formal differential graded algebra. And that's my whole punchline here. If you're interested in derived localizations, right, which you should think of the homotopy theoretical versions of localizations, then you are actually interested in studying thick subcategories of certain, in certain cases, yeah, of certain, like, triangulated categories that naturally arise in representation. So, there you go. That's why we do what we do. Let me say maybe a couple more fun things. You might have wondered, why x cubed, y cubed? Well, actually no reason, it's just very small. Looks approachable, right? But if we take an and we mod out something bigger, then we still have, well, first of all, the bounded derived category is, of course, very different. Well, maybe not of course, but that you have more modules. Anything that's a module for A3 is also a module for A4, so you have more stuff. I mean, you have a lot of stuff anyway, right? But you find all of that in there. Yeah. So also our home, this guy here. So these are different. However, if you're just interested in their derived localizations or the derived localization of that guy, we still have, I made a mistake here. It has to be proper and on 0. Sorry. The 0 one is an extra. 0 one is an extra one. The proper non-zero six subcategories of dB model AM are still just the collections of closed points. Of the projective line. So that's still the same. And what this course is about, so maybe I want to write this down as it is our slogan. The course is about studying the collection of localizations as an invariant. So that's what we're going to do. And the language we're going to use is the language of 6 subcategories. We'll get, hopefully time permitting, we'll have at some point in a suitable part in the course, we talk in slightly more detail how this like inverting of maps and setting stuff to 0 works. But we're going to talk about these localizations in the language of 6 subcategories. All right. So this was the mandatory motivation over. So if later on in the course you think, well, Sira seems to be having a lot of fun, but what is she talking about? Then please think back of this moment here and like realize that, in fact, truly at your heart, you're absolutely right. So we're going to start. Oh, no, that was the right one. We want to keep that one. We're going to start now with part 1, which are lattices and big subcategories. All right, so we're going to talk about lattices quite a lot, and their properties and what this means for us. So we begin with the definition of a lattice. So a lattice is a partially ordered set, L, with some partial order, such that, let me open that. Such that it has binary meets and binary jumps, or binary products and binary coproducts. You can think of this as a category. So what that means is for any 2 elements in L, we have a join the join L join M, which is just the smallest element. So we have a smallest element, C, which is bigger than both of them. L is smaller or equal to C, and M is smaller or equal to C. Right? So that's the same as saying this category, like if you think of this as a category, this pose that as a category, that it has binary products. Binary coproducts. I mean, always take my directions with a grain of salt. I get easily confused. When I say join, I might mean meet. I probably write the right thing. The meet is the dual thing. It's the max. It's the largest element, C and L, right? C and L. That is smaller than both of them. All right, so these things exist. We have, of course, examples. Well, any directed set is a lattice, for example, Z, with the standard order. Good. Then, if we have small lattices, we're going to write them as the Hasse diagram, where the elements in your lattices are just denoted by points, and then we connect them upwards if they are smaller or equal to the other one. So the technical term is like we write an upwards directed edge if and only if the guy up there covers the guy down there, that is, it's bigger than it, and there's nothing in between them. Okay, so if you look at this guy, this is called the diamond. That is a lattice that plays a role, as we will later see. That's the example of a lattice, right? If we have two guys in the middle, the join is the top and the meet is the bottom. We also have the pentagon, which is also going to play a role, maybe depending on how much time we have. I'm starting to think maybe not as much time as we say. That will be the case. Good. So the pentagon is also a lattice. Right, if you take a meet of that one with one of them over there, you end at the bottom. If you take the join, you end at the top. Good. Okay, these are examples of lattices. Now, these are very easy to draw ones. So let's look at some more significant examples that show up naturally in different worlds. So perhaps one of the very important for us are lattices from topological spaces, from a topological space. Example is topology. So we have a topological space X with a topology O of X. So these are the open subsets of X. So then, and this is very important for us, that O of X under inclusion forms a lattice. Right? You just have to check that binary means and binary joins exist. So if we have two opens, then we have that, what's the meet of U and V? It's the smallest open that's contained in both of them. That's the intersection. What is the join? Did I say it the wrong way around? I probably did. The join, you noted, the join is that thing that I just said. It's the smallest open that contains both of them. That is the union. I should be more careful. I'm sorry. The meet is the biggest open that's contained in both of them, and that is obviously the intersection. When I say obviously, it's because if I look at a set of subsets and they're ordered under inclusion, then if the intersection is still in that set of subsets, then it's always going to be the meet. Because it's the biggest subset that's contained in both of them. So if that's a candidate for me, it's going to be the meet. Same with the unit. If it's a candidate for me, it's going to be the unit. It might not be, right? Might not be. You see examples. Good. Another example of the representation theory, which is partially why we're here for, what we're here for.
Would you mind pushing up the other board?
Yes. Thank you for calling me out on that. we have example. Representation here. Let's say we have a ring R, and we have some R module, right R module if you want. You can look at all the submodules of them. This is certainly a coset ordered under inclusion. So what is neat and join here? So maybe first, that we have N1 and N2, two submodules. Then we can look at the neat. That should be the smallest submodule. It's contained in both of them. Luckily, the intersection of two submodules is again a submodule. So we can take that. But what about the join? Well, the union of two submodules might no longer be a submodule, right? Because we might have not enough stuff in there. You should be able to add stuff together from the different guys and stuff. So what we want here would just be the sum of the two. So that is still a submodule, and it contains both of them, and it is the smallest such. Alright, good. Now we're going to give a final example. Maybe I try to abbreviate it a bit, but it's a cute one. It's going to show up again, so we're going to do it. That's an example from combinatorics. What we look at is we start off with a linearly ordered set. You could take Z, and you could take a finite set 0 up to some number n. You consider that under the standard linear order. Then a partition P, right, like that specifically, of L. So what does that mean? That means we can write L as a disjoint union of these blocks Bi, and every block is not empty, right? So it's a partition. Such a partition is called non-crossing. If the blocks do not cross, so what does that mean? We're going to use the linear order here. So it's saying that if we have some sort of interlacing, if we have two elements ij in BL and k BP and KL in BQ, then if those interlace, so we have that I is smaller than K, is smaller than J, is smaller than L, so we have a crossing, as it were, then that can only happen if the blocks are actually the same. Yeah. That's what it means to be non-crossing. Now there's a really neat way to visualize this. You can just put, maybe it's slightly easier to, is it? Oh, okay, we're going to do it. You kind of put your linearly ordered set on a line, and you can connect things that lie in the same block to one another. That gives you some sort of convex region. Maybe if you curve your line a little bit. And these blocks that you get should not cross. So I'm going to draw an example. I'm going to do it on a circle, because it's a bit easier to see maybe. So let's do a non-crossing partition of the finite set. Let's say we have the numbers from 0 up to 8. Yeah. So I could write my numbers from 0 up to 8. On here. And then I could consider a partition. Maybe I put 3 and 4 in the same block, and I just do that by connecting them like so. And I could put 2, 7, and 8 in the same block. And I could do that by connecting them like so. And if I have a fourth block, which perhaps is red, it's bad, like so, then we run into some problems because the blocks containing 5, 6, and 0 and 1 crosses the block containing 2, 7, and 8. Because 2 is smaller than 5 is smaller than 7 is smaller than 0. Okay. Started in the wrong place, but we get to fit this. But so this is crossing. All right. Now, the beautiful thing is that by Rivera's we know that the non-crossing partitions so NC of L, that's the set of non-crossing partitions, is a lattice. On the reverse refinement, that's the standard order one usually puts on it. Just look at it on the refinement. It's also a lattice, it's just a dual lattice. So what does that mean? We have that two non-crossing partitions can be compared such that P1 is smaller or equal to P2 if every block in P1 is contained in some block in P2. Yeah. For every block in P1, there exists a block in P2 containing it. And obviously, this is a lattice, so perhaps we don't have to go into detail here, but if you say these are actually two distinct partitions, the white one with two blocks 3, 4 and 2, 7, 8, which are big and the rest are just singletons, and then we have the red partition, which is just one block 0, 1, 5 and 6, and the rest are just singletons. If we take the join of those two, it's not as simple as just taking the union, right? So what instead you do, and I'm just going to do that in this picture, and you're welcome to work out some examples if you want. Write down the general rule. You're going to melt any blocks that cross or touch, right? You're just going to melt these blocks together. And that's going to give you the join of those two non-crossing partitions. In terms of the need, it's a little bit easier. You can just go and intersect your blocks pairwise and see what you get. Okay. But maybe we'll see a little bit more of, we'll see another example of non-crossing partitions later when we talk about fixed subcategories. So we're going to do that again in the next example. All right. So maybe I should tell you a little bit more an important property of a lattice. So, right, we said a lattice is a poset which has binary joins and binary meets. But of course, that also means that it has all finite non-empty joins and all finite non-empty meets, because we can just iterate this. Yeah. However, you might not have finite, you might not have empty joins and empty meets, and you might not have bigger joins and bigger meets, right? So that's a specific conditions we can have on a lattice. A lattice is complete if and only if it has all joins, all set, or all small joins if you want, right? I mean, if you're a set, you're good. Yeah, it has all joins and all meets for just maybe a little bit of notation to make it very clear. If we have a subset S of a lattice, there exists a join of S, which is the minimal element C, such that S is smaller or equal to C for all elements in S. And we have a meet, which is the maximal element C that is smaller or equal to S for all elements in S. Okay, so if we think back maybe of our first two examples, then we see that the diamond and the pentagon are certainly complete. Yeah, in fact, any finite lattice is complete, right? Because it has certainly all, like, if you take any subset, any non-empty subset, this certainly has a meet and a join, just by iteration. What about the top element? Very good. If you're a finite lattice, you could just take it as the join of everything in your lattice. But that's an excellent question. I was just going to say that next, so thank you for taking that. So in a finite lattice, you have the top. You can't just take it as the join of everything, which is nice. But normally, right? Normally this is not the case. A lattice might not have a top and a bottom, for example, here, right? So arbitrary joins, arbitrary meets do not exist. Usually, what's the join of the even numbers? That doesn't exist. What's the top of this lattice doesn't exist. At the top in general is defined as the empty meet, right? Because it's the smallest element, it's the largest element that's smaller or equal to well nothing, right? It's like, there's an empty statement. The top is always the empty meet, the bottom is always the empty join, and so this is not complete here. Now, I just put that in. So we're aware, maybe in nature, you're going to find lattices that are not complete. The lattices we're going to discuss in this course, they're all going to be complete. I say that very confidently now, but I take the freedom to maybe have an example at some point, but probably not. The ones we're interested in are complete. In particular, that's maybe important to notice is that O of X is complete. All right, if we have a subset of opens, if I write O of X is always the lattice of opens of the topological space X. Unless otherwise stated X is a topological space, for now. So when we have that, okay, certainly if I look at the join, that's fine, that exists, yeah? Because that's just the union of all of them. And we said if the union works for a join, then it's going to be the join. If the union is in my set, then it's going to be the join. The union of all of these things is an open subset. That is the join. But now we're like, but wait, what about the meet? Of course, I'm not allowed to take arbitrary intersections, yeah? Of opens, might not be open again. However, what do I do instead? Yeah? I look at the intersection, that might not be open. But it's going to have an interior, which is the largest open that's contained in it. And that is going to work for us. This is the interior of the intersection of all of the UI. All of the UIs. This is going to be, because that is the biggest subset of X that's contained in all of these opens, so that must be the biggest open subset that's contained in all of them. Yes?
So this suggests that sort of for any lattice, if you have all, okay.
No, say it.
If you have all joins, for example, or all meets, then you also get the other by this specific.
Beautiful. Beautiful. That's exactly what happens. A lattice is complete
Just the statement that presentable categories have limits.
Exactly. Except easier, because we only need positions. A lattice is complete if and only if it has all joins, if and only if it has all meets. So you only need to check one of them. Yeah, that's not going to work for lattices, for a lattice which is not complete, right? You might have joins, binary joins, but not binary meets. You really need to know it has all of them. Why is that? You just told us, right? Because what can you do? Let's say we're just going to do one direction. Let's say we have all the meets. Then what's the join of S? It's going to be, it's the other way around to see something new. What's the join of S? It's going to be the meet of all the guys that are bigger than everything in S. And that exists, and you can think it through carefully to convince yourself that this is in fact the join. Right? When you check something as a join, you have to check it is really bigger or equal than everything in your set, and then you have to check as a second thing that it's the smallest guy that satisfies. Then you're done. Right, so complete lattices. Very nice. Good. So in the last 10 minutes of the talk, we're getting to our star player. And that's the lattice of 6 subcategories. I do have 1 hour, right? That's correct?
Yes, yes.
50 minutes, so I have to stop. So, 6 subcategories. Right, so we have K, a triangulated category. And a lot has been said today. I should absolutely work with the enhancement. Right? We had 2 very convincing talks in that direction. I feel like at some point there was the word old-fashioned being used in connection with people working with triangulated categories. So we got to go there. I don't need an enhancement. Yeah. So I'm not going to have an enhancement. If you want an enhancement, have your enhancement. It's all going to work. It's fine. It's fine. All the categories we work with are algebraic. I think, yeah, sure. And the explicit examples, but yeah, just do it for a triangulated category. Nice and old-fashioned. So this is an additive category. We know this, but we make sure we're clear how we write things, what we're dealing with here. Right, so we have an autoequivalence called a suspension. And we have a class of diagrams that look like so, called distinguished triangles. I'm just going to write triangle when I talk about distinguished triangles. Satisfying a whole bunch of axioms that loosely try to emulate a little bit exact sequence. And of course don't, but yeah, we know that. So we pick our favorite triangulated category, maybe throughout, just in case I forget to say that later on. I will want them to be essentially small, which in practice all the examples I will talk about are essentially small, so that is fine. That is just, when I talk about lattices, I want the lattice to be a set. Yes. So what I'm doing is I'm considering 6 subcategories. A 6 subcategory of K is a, and whenever I say subcategory, I guess I mean a full subcategory. I think there's nothing else I need to tell you here. A full subcategory such that it is closed under a whole bunch of stuff, closed under, put that up, and it's closed under the action of sigma, the suspension. So if I apply, did I give it a name? No, a subcategory T of K. So sigma of T is just T, it's the same as sigma inverse of T. So it behaves well with respect to the suspension. Apologize for putting that down. I'll switch the boards as soon as possible. It is also closed under the 2 out of 3 rule, if you want. If you have a triangle of x, y, and z before, that's A, B, and C now. If 2 of A, B, C are in T, then so is the third. It would be enough to say it's closed under cones or whatever co-cones, but it just amounts to being closed under 2 out of 3. And then finally, one additional thing we're going to need is that it's closed under summits. Okay, and we're going to see, I presume at the start of my next lecture, why these big subcategories are natural things to study. You already start to think, I mean, right, if we were to define a sub-object of a triangulated category, it should be a triangulated subcategory. It should be closed under suspension, and it should somehow be closed under making these triangles. So it should be definitely closed under the first 2. That's just if you naively try to define a sub-object in a natural way. There's also a very good reason why it should be closed under summits, which we're going to see. Say again? Yeah, I mean, if you kind of want to talk in that language, it's closed under retracts, yeah.
You should also maybe include 0, right?
No, I don't think I have to, right? 2 out of 3. I have to have, okay, it's non-empty maybe.
Right,
it's non-empty.
But
it's non-empty.
Right?
It contains 0, yes. Yeah. So if you have something in there, you're going to have 0 in there, right? Because you have A equals A as a 0 cone. Good. I mean, you need it to be non-empty. Is the subcategory not always non-empty? I feel the subcategory is non-empty.
No. In this context, sure.
Is it?
It's a full triangle.
Non-empty. Yeah.
It's not full about.
Yeah, you're happy. Everyone's happy. 0 is automatically in there. Yeah. Good. So I promise you to put that up.
The empty paper is not triangulated.
Yeah, but it's closed under the action of sigma 2 out of 3 as an additive subcategory. You know, good. As long as you're non-empty, everything you desire is going to come to pass. It's very nice. So let me just finish with an example. Then, maybe I'm going to say a blanket statement so that it's going to get held against me. I don't think I need it. Oh, yeah. K is a field. K is always a field. Yeah. If you wanted to be algebraically close to A, but I don't need it for now. Yeah. I take one of these beautiful categories that were defined by David this morning. I take a bit of a smaller one because I'm lazier than David. So we take A2. Yeah. And we've seen you didn't use the word because you were gentle, you didn't use fancy words, but what the Ausländer right equivalent of that looked like, because that thing was just equivalent to this mesh category, right? And the mesh category here is easy. So this is my module category of KA2. And then I do that together with a bunch more copies of itself, yeah? Just living in different homological degrees, something like that, yeah? So let's look at 6 subcategories we can get here. And I'll tell you along the way some things. So we always have 0. Right? And we always have k. That's something we don't have to think about. What else do we have? Let's say we have an object in there. Let's say the vertices here, they're the objects, or indecomposable, the classes of the equivalence, what I want to say, isomorphism classes of indecomposables, they're just the points in here. So if I take the blue guy, let's call this P1, then what is sigma of P1? We know that from David's lecture. This is over here. And then sigma inverse is here. And then you have a bunch of copies to the sides. But one thing you see, maybe, is that you're not going to have maps of any degree between P1 and sigma P1 or P1 and sigma inverse P1, let alone anything that's even further away. You don't have any homs, you don't have any x1s, you certainly don't have anything more because you're hereditary. So if you think you have to close this thing and under all of these actions, you close it under the action of sigma, 2 out of 3 doesn't buy you anything new, and summons doesn't buy you anything new because you're already indecomposable. So this is really just this, all of these objects, the additive closure of those. So that's the 6 subcategory generated by P1. But what if we throw, we can repeat that for any other of our guys, right? Because the others behave exactly like P1 does. That guy, P2, he's here. So we get this 6 subcategory generated by P2. And a third one, S2. We get a 6 subcategory generated by S2, and they don't interact. Well, they do interact, of course. So how do they intersect? They intersect trivially, right? Because if you look at the blue dots, they don't overlap with the red or the violet dots, so they intersect trivially. But what if I take the join of 2 of them? What if I take the join of the blue guys and the red guys, perhaps? So what I see here, I have a map from the blue guy in here to the red guy in here. What is the cone of this map? Well, you know, in general, you maybe have to work this out a little bit, but the beautiful thing is we have it in the picture. The one you think it is, it actually is. It's precisely the purple guy down here. So you actually, if you just have 2 of those, if you have P1 and P2, the purple guy comes for free as a cone of a map between the 2. Now, if you instead take the blue and the purple one, you can get the red one in the middle as an extension of the 2. And in fact, whenever you pick any 2 guys and it starts to become a bit symmetric, you get the third using this 2 out of 3 property. So the lattice of 6 subcategories of dB mod Ka2 is just a diamond. So this very simple lattice, we can actually realize it as a lattice of 6 subcategories. And this is my time to stop. Thank you very much.
Are there any questions or comments for Sira? Yes?
So it's not distributed.
No.
This is going to be an issue.
This is going to be an issue. Yeah. Well done. This is a little bit of a spoiler, a little bit of a trailer for future discussions.
Does having on needs make a difference?
I'm sorry.
Does having on needs make the empty need?
Yes. Yes. Absolutely. So if you have all of them, then you also have the empty one. So in particular, you have a top and you have a bottom. Very good.
I kind of don't yet understand how your non-crossing path example features.
Yeah, I was really going fast here.
Maybe a simple question, is this lattice distributive for any linear?
No. And I picked take these examples for reasons because they're not distributive. And this is like, I mean, this is going to be a punchline, but maybe you feel you want it. You want it. And right, if you are distributive, we are going to show that if you are distributive, that is enough to be controlled by space. And that is the situation that maybe you're used to from 2D geometry, or you know, stuff like that. I don't know. There you have distributive things. If you work with examples from representation theory, in general, you do not have distributive things. There is a very important obstruction that I hope I get the time to mention. Yes, not distributive. David?
It's a philosophical question, but is there a reason why this possible representation theory so much, this non-distributivity?
Yeah, exceptional collections. If you have a kind of an interesting exceptional collection, it automatically means that your lattice of the subcategories is non-distributive. Because then, I mean, I feel like I'm spoiling everything. No, this is fine. Like non-distributivity, actually, non-distributivity of a lattice is equivalent to having either this diamond or this pentagon we drew earlier as a sublattice. That's enough. And so, if you have an exceptional collection that's nice enough, you're going to find the diamond as a sublattice.
Any further questions or comments? Go ahead.
This might be a stupid question, but like the algebra that we are working on, we are still on like thinking algebra. Like, is this whole theory only applicable to have victory algebra? Or?
Is it? I'm sorry, I didn't.
The whole theory of like derived bounded category of like the A modules that you are considering, is it only for hereditary?
No. I mean, anything like that. I mean, all the examples I show are hereditary. Right? They're kind of easy to handle and write down. Well, sometimes, but the theory is going to be for general. I mean, in fact, I'm talking about the categories I know and love. I'm used to, but I think there's a lot to be said of constructing different examples, looking at different examples of triangulated categories. So all I need in theory is an essentially small triangulated category. And then I studied the lattice of 6 subcategories. And for example, some representation theory, I can tell you what they are. But if you have another favorite triangulated categories, knock yourself out and see what you get there.
I was wondering whether the global dimension shows up in the drawing, like the levels, or maybe
In which drawing?
Here.
No.
On the right. Yeah.
No. No. Because if you just go to A3, I just didn't do it because I'm lazy. You still get a very very layered guy.
Okay.
So no. But it's an excellent question. Yeah. It's not so easy to try.
Right. Let's thanks Sira again.